these DC theorems, like dealing with Thevenin and what call this superposition, Norton, whatever other. It's very important to know your basics. It is very important to know your basics. Knowing your basics can be the difference between getting things right and messing it all up. Now, if we look at, let's take a simple example. What you need to really be careful about are these things. We already dealt with some of these in some scenarios, but I want to raise particular attention to them. Now let's look at open circuits. Open circuits. This is specifically how these open circuits affect the what call this our calculations. This is basically basics, but a lot of people don't have these basics. So I just wanted to what you call this, to dissect them. Now also what can be tricky is what you call this short circuits. Short circuits. You need to understand your basic Ohm's law. Ohm's law. You need to understand Kirchhoff's. I always have a problem spelling this guy's name. Kirchhoff's voltage and current laws. All right, but also feel like it would be good to understand. But I'll deal with situations where we're using two sources or more. But if you understand your open circuits, understand your shorts, and you adhere to your Kirchhoff's and Ohm's laws, you are going to be a little bit more safe when dealing with this. Let me take an example. Let me say I wire a circuit. Let's do this. Let's wire a circuit. The direction of my, yeah, that's better. That, let's say we have a circuit like this. Now let's suppose I were to supply a resistor here, right there, okay, and then probably a network of resistors. Let's say something series parallel. Why are you curving like that? Something series. I'm struggling with the straight lines. Something series parallel like that. Let's suppose we're dealing with a case like this. Okay, now this is let's call this R1, R2, R3, and R4. Maybe R load can be any one of these. R load, we can decide that it's any one of those. Now, if we are going to do the circuit like this, there, remember when we're doing let's look at Thevenin. At one point we say we replace the source with an equivalent resistance. Both Thevenin and Norton, they do this. When you're calculating the resistance is, we say we replace the source with its equivalent resistance. Let's suppose R3 had been our load. Let's suppose R3 had been our load, so it was disconnected. Okay, disconnected there and there. All right, let's suppose this had been our load. Now, it means therefore I would have points A and B here to show this is where I actually remove my load. Okay, just to highlight that this is where I remove my load. All right, you see that now. This still gives us a scenario where we have R1 in parallel with these two resistors now. Okay, so when you're calculating our voltage at that point, we need to know that is the voltage across across R4. Right, in any event, if you put this back, our voltage across this is the voltage that would have been across R4, because the two would have been parallel. But anyway, my point here is this: when you replace this voltage with an equivalent resistance, that would be a zero. That would be a 0 ohm resistance, which is basically a wire. What have I done? Essentially, I have actually short circuited R1. R1 is now removed from the circuit. I've dealt there was I have one video I made previously where I was dealing with what with how short circuits would affect a resistor such as in this scenario, such as R1 in this case here. We will remember that I call this a what? A 0 ohm resistor. So this was an R of a short, and this is 0. All right, it's a wire. Now, if we then say we want to have the total resistance here for this scenario, let's call it R parallel. Our R parallel, this is because of the supply. Our R parallel there will really be 0 times R1. Doesn't matter the value of R1, that's still going to give us a 0. Right? Over 0 plus R1. Again, doesn't matter the value of R1. Our total here, our parallel resistance will be 0 here. What does this essentially mean? Remember, in that topic where I discussed where I discussed shorts, I did say if you try to get the current here, the current that would be flowing here. Suppose there was a source from somewhere. The current that would try to come here. Let's suppose we had a supply somewhere. Let's just imagine a supply. All right. Sometimes we have to think outside the box. Now, let's suppose there was a supply and we're getting a thing. Forget this scenario. Let's suppose it wasn't this. There was a source that was giving us a current there. Let's call it I imaginary. All right. Let's imagine a current that is coming in there. We'll say that current will have been split between these two. And you see how now, if you are going to calculate the current through this, you have to say R1 over the total. That's the what call this 0 plus R1. That gives us 1. Okay, this is R1 over R1. Okay, times the current that is coming in there. What does it mean? All the current. Remember, we have said when you're looking at when you're looking at the current divider, we say that when we want current in this leg here, we use that resistor there. Okay, because the value rejected. This is when you deal with current, we talk of rejection because resistors reject current. So we do a ratio of rejection. So the current rejected here goes there. So we are calculating the current rejected there, and it's going to go there. That is the what? That is the current that is going to go to what? To IRS is equal to IRS. So the current through the short. All right. So the short, as you can see, will have the whole current. What does this mean? It means if all I1 comes in there, this here is actually a 0. There's no current on that leg there. What does it mean? It means this guy is it's basically not part of the circuit anymore. So a short is that undesired what effect, unless by design there. But I don't know why we would have that such a design, because this would be a waste. All right. But I will still say, unless by some stupid design you intended to have a short, then that short would what would actually remove that load there. Right. So what the job of a short, as you can see here with this explanation here, the job of a short is to basically remove the current. All the current will go through the short. Meaning, if you go back to Kirchhoff's laws now, you say if I1 came in and all I1 went to the short, it means nothing will go there. It's as good as what? As that circuit being broken. So that is one scenario that I would like to think. I actually started there with what? With the short circuit. Okay. We already dealt with the scenario. Remember a specific example that was dealt with when we were looking at Norton. I think it was a few resistors here. A few resistors there. I think it was a network like so. Something like this. There we had, I think, something else there, and then we had our load there. Okay, our RL was after so many resistors. This would have been our RL. Now, what happened is, obviously, when you're doing with when you're doing with resistance for Norton and for Thevenin, we would remove the load. Okay, having removed the load, that there is our what? Is our point of connection for the load. Then we analyze the whole circuit and say what does it supply at this points here in terms of voltage and resistance that looks into those points. Now into that that looks out there at point A, B. So this is an open circuit. The open circuit at the result that no current could flow. Current only flows through the closed circuit. So this is an open circuit. So current through this resistor here would therefore be what? Be equal to nothing. What did it do? Yes, it killed the current there. It killed the voltage because V being equal to IR, according to ohm, again there is ohm, V being equal to IR, it means therefore there is also no voltage drop here. So that means if this is 0, 0 times R, so voltage will also be 0. So there will be no voltage. So the short has the what? Has the effect to what? To the short has the effect to cut out what call this resistors. But the what call the but the I'm busy right now, so I'll see this later. The short has the effect to what? To actually cut out the resistors, but the open does not cut out resistors. What it does is what? It cuts out the currents and the voltages. This is very critical to understand. In some examples, when you look at this, it will be very important to understand these two basics. So understand how the short affects the circuit, understand how the what? The open affects the circuit. And please bear in mind, remember what? To adhere to these two laws here, primarily those two, Ohm's law and what? And Kirchhoff's laws. Let me look at, I would like to go into a few examples. Probably let me look at an example that comes from some book here. Let me look at, let me look at, what you call this? Let me do this. Okay, let me look at a circuit like this, where this becomes a little bit important. Let's check a bridge. Okay, let's look at the Wheaton bridge. And then let's say we have typically we have our laws there, but nothing stops an examiner or a teacher, an assessor, from asking you to analyze your circuit from a different perspective. Probably call any one of these resistors here the output, the output, yes, the load. Now, if we look at a scenario like this, what you see is if we remove this resistor, let's suppose we remove, our load was that resistor there. If you are going to deal with the resistance, it means therefore this circuit, if we were to redraw this, because sometimes redrawing makes the circuit look a little bit friendlier. This is a line, I can make that line continuous, and this, let's call this R1, R2, R3, R4, R3. Okay, that can be R3, no problem. Let's suppose we had a circuit like this, and this is our load in the middle there. Now you can see that from the positive, we can draw our R1. We draw actually our R1 and our R2. They are drawn positive. Okay? These two are drawn from the positive. Now the RL joins them. So the RL could be actually a, sometimes these diagonal lines can confuse people. Not really, that is, this will be our RL. And then we'd have the one side of where R1 connects with RL, it connects also to R4. So this will be R4. And where R2 connects to RL, there is R3. So R2, no, not the R2. R2 connects to RL, yes, there's R3. R2 connects to RL. It's like two twos there. There is R3. Okay, so basically that side is connected to the negative. So this is the same circuit. It's very, sometimes it makes things, oh, okay, things would look easier if you read through. Doesn't mean you must. If you can see it without doing it, it's fine, but it sometimes makes things look much simpler if this is done. Now if I'm to remove the RL now, because when I'm doing the resistances I have to remove RL. Okay, but these are my points now. This will be point A, that will be point B. So obviously if I have a supply here, V supply, These are two parallel circuits. V supply is across R1, R4, as much as it is across R2, R3. Right. So these two are sharing V supply. Those what? Those two are also sharing V supply. So if I wanted the voltage at A, remember we always measure with reference to the negative. So the voltage at A there will be what? Will be the voltage across R4. Voltage at point A is the same as voltage across R4. In that case, we mean R4 over the total R1 and R4 times the supply. Okay, and VB also is the voltage across R3, because between R3 is between B and ground, so a negative. So that will be the voltage across R3, VR3 is very important to analyze, to be able to analyze this correctly. V3 or R3, I just want to be consistent. Okay, V across R3, and that is given by R3 itself over the total. These two are sharing, these two are wired across the supply, so these two are sharing the supply. That will be R2. This is just our voltage divider, R2 and R3 times the supply. This is just the what? The voltage divider. All right. So it's very important to know this. So now, what will be the voltage between A and B? What is the voltage across AB? That will be VA minus VB. All right. I'll say the modulus. Why? Maybe VA is smaller. In which case, I don't want to make that voltage a negative value. All right. So our VAB will be the modulus of the difference between VA and what? And VB. Because I'm doing this just in case the VA will be smaller, it will not give us a negative value. So the positive of the difference, right? The positive of whatever difference there is the voltage across what? Across RL. I don't know whether this, remember VAB is our what? Is our, would have been our what? Our Norton voltage, or our what called, or our Thevenin voltage, depending on which one you were looking at. Remember, we really not really Norton voltage, the Thevenin voltage, because Norton you would have to get the current. Okay, it's more important to get the current with Norton. Yes, we do this to what? To get the resistances, but we really don't know about voltage when talk of Norton. But as for Thevenin, that would be our voltage for V Thevenin there. So this is more relevant to say VTEV would have been found like that. That would be the difference between those two. Now, when we now talk of the other scenario is where VS is replaced by its equivalent resistance. All right. Why am I writing like? Why is that a Q? All right. There is my. I have replaced. This is my what? My V supply. I have replaced with an equivalent resistance. Now, when I come and I say there is R1 and there is R2, R4, sorry. Why are you going up? It's a little bit difficult to use these instruments. All right, this is R2 and R3. Okay, so look at this. Our A is there, our B is there. So if I'm now going to look at this now, how does it affect the resistances now? Remember our Thevenin and Norton are calculated the same. R Thevenin, R Norton, the calculation is the same. So this would be the run from what? This would be R from A to B, the run from A to B. If you look at the circuit, if you want to analyze the circuit, let's take A as a point. A is a point where we have a split from A. That split, the one root from A is R1. The other root from A is R4. There. When I'm leaving A, I either go through R1 or I go through R4. Where do I go? I go to this wall. This is now one thing. So it's like there is a join We join R1 and R4 are joined through VS there. So there's a join there. Okay, so this is through VS. Now there's a join there. From there, from that join, you either leave via R2 or you leave via what? I didn't say R3 here. Or you leave via R3 to go to B. So from this join here, there is a further split. But this split here, you either go through R2 or via R3. And you go to a point, they join together, and that point is B. So basically what it means here is our RRAB is simply R1 parallel to R4. This in series with let me move it first. This in series with, I have my pen, R1 parallel to R4 in series with R2 parallel to R3. That shouldn't be difficult to do. Okay, so it's R1. If you leave here from A, you either go through R1 or R2. So it's a split. You either go through R1 or R4. So I meant to say not R2. From A, either it's R1 or you go the other way and it's R4. So easy from A, you either go through R1 or R4. You join together. They join A, the other side of A and the other side of what? The other side of R1 and the other side of R4 are joined together. So we join them together. Now, however, from that join, we have a pathway through R2 and another pathway from that join through R3. So two pathways, so it splits again. It either goes through R2 or it goes to R3. And then they join again at B. They join again at B. So this is basically, so it's very important to analyze this properly. I hope this sunk in. I'm going to also do another example with a bridge, because this is very, very, very critical. I'm going to do another example with a bridge, but I'm going to take aside one example with the side will basically work for any of the others with the side, all right, or from the side. So what I'll do is, hopefully people understood this, and therefore it is, if your values here, all you do is do your what? R1 times R4 over R1 times R4 plus, because it's in series, plus, but then there's a parallel again, R2 times R3 over R2 plus R3. So our resistance here is basically not that difficult, all right? So let me hope that this sunk in. Let me hope that you see how to analyze. When you're analyzing for what? For the voltage, it was important to know basics, that your voltage at that point here basically will be the across what? Will be the voltage across R4, because our negative is what? Is on the other side of A. On the other side of R4 we have A, on the other side we've got the negative, so it is the voltage across R4. Same story here, the voltage at B is what? The voltage across R3, because on the other side we've got ground. Okay, normally we ground our negative. Unless the grounding, unless we are dealing with negative voltages and we've grounded the what? We've grounded the positive. It's possible that sometimes our supply is what? We need a negative supply, so we ground the positive. But I want to keep it simple. Let's just think of it that way.